Do we live in a flat world, or do we live on a ball hurtling through space? Some will say yes to the ball, some will say no to the ball, and that we live on a flat world. In this video, I will be debunking, or at least showing the error of the way of 5 flat earth proofs that are often bandied about by flat earth people to prove that the earth is flat. I'll be showing that they don't in fact actually prove that the earth is flat. They don't hold up to scrutiny. Now, one of the arguments of the globe earth people about this particular map, this is a flat earth map using the azimuthal equal distance map, which means a line from the center here to any geographical point on the map is the actual distance from the center to that point. Of course, being a circle, the problem with this is lines that radiate out get wider the further they go. This means in this instance here, Australia gets stretched, and the globe people will often say, this map is so wrong it's not funny because Australia is not that big. Why don't you get a map that works? I'm going to address that in the next segment, but I also want to show that we can suffer, all people, all sides of this flat earth, round earth debate can suffer from a logic fallacy. Let's have a look at the logic fallacy first, then the erroneous map that the globe earth people are in fact using, and then we will debunk the 5 proofs. And if you want to go straight to the debunking, just use the timestamps in the description below. But first we'll have a look at this photo and we'll talk about a logic fallacy that applies to lots of things, not just this particular flat earth, round earth debate. So here we have a photo of 4 people sitting against the wall. What do we notice about these 4 people? They're all smiling. We notice that. They are all wearing jeans. They are all interacting with an electronic device or mobile device. The 2 men have dark hair. The 2 women have light-coloured hair, even if it's not natural. We also notice that the 2 people on the left, on this side, have lace-up shoes. We also notice that the 2 people in the middle have tops that are undone, and we notice that they're sitting boy-girl, boy-girl. We also notice that none of them are sitting with both legs straight out. They have their legs bent up, so their knees are slightly raised. Now, I'm about to put forward a few things here, conclusions that we can draw from this photo, absent of any other information, including experience we might have. This is all the information we have, so we can conclude the following. Sitting against a wall makes you smile. Sitting against a wall makes you raise your knees up. Sitting against a wall makes you use electronic devices. Only people who sit against walls and use electronic devices smile. Smiling means you will automatically sit against a wall. Only people with jeans sit against walls. If a group of people is sitting against a wall, they automatically go girl, boy, girl, boy. If such a group does sit against the wall, the 2 people in the middle always unbutton their shirts. I'm sure, and we can also add that people who sit against walls wear shoelaces, or shoelace wearing makes you want to sit against a wall. All of those are completely false, and we recognize them as the idiocy that they actually are. However, the same logic fallacy applies to many things, where a group of results is observed and then conclusions are drawn on those without actually realizing that they are falling into a logic fallacy. Now let's have a look at this particular map. I want to draw your focus to 4 or actually 6 countries on this map. The first 2 will be Greenland, Australia, Russia and China. Then we have Poland and Iceland. Now we are all familiar with this map. This is a map that we all grow up with. It's in the atlases that we have at school. So this is the world map that all the globe people like to have in their paper atlases that they open up at school. Now I'd like to show you something interesting. These numbers are in the million. They represent the square kilometers of these countries. So Russia has 17 million square kilometers. China has 9.6 and so on and so forth. Now just have a look at the size of China on the map. How many Chinas can fit into one Russia? You would have to say possibly 4 Chinas, going by how it looks on the map, would fit into one Russia. However, when we have a look at the distances, the square kilometers of the land masses, we see that not even 2 Chinas actually fits into one Russia. When we have a look at Greenland compared to Australia, we see that it's 2.1 million square kilometers versus Australia's 7.7 million square kilometers. However, it looks like Australia could actually fit into Greenland, but that is not correct. That means the Greenland size here we have on the map is completely out. 3 Greenlands can actually fit into Australia. However, this map would show otherwise. Now we'll have a look at Poland and Iceland. They look very similar in size. Poland is 312,000 square kilometers. Iceland is 103 square kilometers, meaning 3 Icelands can actually fit into one Poland. And yet, here in this map that we all grew up with in school, it shows Iceland is the same size as Poland, and there's no way 3 of these would fit into that. What this means is that this map that we have all grown up with is also completely wrong. So when a globe person says to the flat earth person, get a map that works, meanwhile, this is the map we all learn about in school. Now there's one other really interesting thing about this map, and that is the shape of Australia. I'm choosing Australia because it's where I live. If you live in the United States, you choose the United States. It doesn't matter where you live. If you live in Poland, Germany, if you live in the UK, it doesn't really matter. You can do the same experiment. And that is, if someone was to ask me what is the shape of Australia, and I drew this, roughly speaking, or I said, this is the shape that we are shown in books. And then if they said, do you know if that is the shape for real? I cannot answer that with a yes. The reason I cannot answer that with a yes is because I do not have map making skills. I do not have a boat or a yacht or some kind of craft to traverse or travel all around Australia with my map making skills, plotting points, to actually determine if this is the shape of Australia. In all honesty, I do not know, and I have no way to prove it. What about India? Is that the shape of India? I don't know. I cannot prove it. What about India's location to Australia? Is that accurate? I don't know. I cannot prove it. I cannot get on an aircraft and follow compass bearings and end up in India and say, yes, the compass bearings told me I was travelling this way. That doesn't prove that this is the location. I don't know how far we were going this way. I don't know what anomalies are within the plane that might be interfering with the compass bearing to make me think I'm heading in the right direction. The truth is, if we are all going to be honest, individually we do not know if any of the land masses actually look like this. We take it for granted that they do. but we do not honestly know. Deep down, we would have to say we don't know if that's the shape of the country that we individually live in. We don't know. I'm led to believe Australia is 7.7 million square kilometres. That's according to Wikipedia. However, I don't know if that's actually true or completely bogus. I don't know if this is the shape of Australia, truthfully, or completely bogus. What I do know is that if I believe this is the shape of Australia, I'm taking it on faith that the original one or two people that did the map outline when they apparently sailed around, plotted points, were in fact telling the truth and not making up a shape. That is what I'm putting my faith in those people. Okay, so we've had a logic fallacy and we've had evidence that if we are honest, we don't truly know a lot of things about the world in which we live. Okay, now having said that, now let's address 5 of the flat earth proofs that are actually not flat earth proofs. Now the first proof we are going to address is the flat horizon always reaches up to eye level, whereas the curved ball would actually see us looking down. So if we are going to take this by way of an example, we have a person here standing on the ground and they are on a curved ball. Correct. This is their eye line. However, on the curved ball, they would be looking down. So at first glance, this seems like a very logical thing. I would be looking down. The problem is we don't stand on a land that is curved so greatly, which would actually see us looking down. And so now we come to the first problem of this. If the horizon is flat, if the world is flat all the way out, I have a distance that I can see. We designate that as the horizon line based on my height. Flat earth people will say this is partly due to perspective because I'm so close to the ground. Now, if this is my horizon limit of sight, I am still actually looking down because it's flat. It just appears to come up to my eye level due to perspective. Now let's have a look at what the Debunk calculator says when we throw in a few ball numbers and we test the angle. Remember that the angle from the eye here stretching out this way will be a right angle if the horizon meets the eye level. But I've just shown you, you are actually looking down just slightly even on a flat horizon, whereas the argument is this little angle here looking down would be less. So let's clear this off. So let's check out an Earth calculator that actually shows us the angle we would be looking at. Okay, I've already put something in here. I'm saying that the viewer's height is 6 feet, which is 72 inches, and it's giving me a few little things here. What I'm really interested in here is the angle to the horizon. So the geometric horizon is 3 miles, the refracted horizon is 3.24 miles. We can ignore the refracted one for a moment because that's talking about the light refracting. We're just going to go to the geometric horizon with no refraction. So a 6 foot tall person, the horizon is 3 miles. Okay, but the horizon dip to the eyes is 0.043 degrees. In other words, you will not notice that from what I would say is perfectly flat, which would be 000 degrees. You will not notice that. The angle between the eye level and the horizon here we go again, is 0.043 degrees. Okay, let's change this. Metric, that won't change. But let's go with metric that I'm 250 meters high. 250 meters, we can have a look at that imperial, is 820 feet. Okay, so I'm 250 meters high, 820 feet. The horizon dip is half a degree. Half a degree. What if I'm a quarter of a mile high? The horizon dip is 0.6 of a degree. It's not even 1 degree. So I'm quarter of a mile high. I'm looking out to the sea at the horizon, and the dip is only 0.642. In other words, from my perspective, it will look at my eye level. And to add further to that, the horizon at that point will actually be 71 kilometers away or 44 miles away. What if we go higher? What if we go to the height of an aircraft, which is 10 k's up? At 10 kilometers high in an aircraft, the geometric horizon is 350 kilometers away, and my dip to the horizon is 3.2 degrees. In other words, my level line, instead of being 90 degrees, is only 86.8. And I defy any person to know, if they are in an aircraft looking out, if they are actually looking out at 90 degrees, or if they are looking out at 96.8 degrees, almost 97. You would not know. And in terms of miles, we're talking 221 miles here. So the idea that the higher I go, the horizon comes to meet my eye level, the differences in these degrees variation of dipping to the horizon doesn't match. Now, we have heard of things going 40 kilometers up or 100,000 feet. So we go, there's 100,000 feet. At 100,000 feet, the dip to the horizon is only 5.5 or 5.6 degrees. And in terms of metric, we are talking about a view height of 30 kilometers high. So at 30 kilometers high, the horizon is 624 kilometers away, and it's 5.6 degree drop. Again, at that height, when you see footage from the balloons and all this sort of a thing, you do not know. It's a camera. Which way is the camera angled? You cannot say 5 degrees of a camera. You will not actually know if a horizon is 5 degrees. Now, the additional problem with going to these extra heights, for instance 18.4 miles or 20 miles high in this example, is that you have the cloud cover. Now, if you assumed or took, for example, that clouds might be as much as 10 kilometers high, and in metric we are 30 k's high, in that case you're only 20 k's above the cloud cover, and that's going to change your perspective again. The whole point here is that to say that the horizon rises to eye level only on a flat world doesn't actually wash, because on a round world, as you can see here with this calculator, the change in degrees as you go up is that minimal that you as a person won't even notice it. You can sit on a plane 10 kilometers up, look out of the window, and you will not know if you are looking straight out at 90 degrees or if you are looking out at 86.8 degrees. You do not have the minute adjustments enough in your senses, let's just say, to know if you're looking at such a minute difference. You just do not know it. And considering that the horizon is so far away, and by this point at 357 kilometres away, or 221 miles, it's all hazy and fuzzy anyway. So that is number 1 debunked. Let's move on to number 2. Okay, number 2 is that when I go to the shoreline, everywhere I look, the horizon is flat. And what you will sometimes also see at the shoreline, for example, we have some beach, let's just say, then sometimes you might see a flat earth experiment, and I will give kudos to all the flat earth people for actually experimenting here. And in this experiment, they put a plank of wood or a level on a trestle of some description. We'll just call this a level so that we can have a really good idea of what they're doing here. So anyone can walk up and they can see that the level is level. And then the idea is, we're talking, this is the water, you will find that you can bend down depending on your height, and you can check the water horizon against the level, and you can see that, oh my goodness, this is a level, and I can clearly see that if I stand here looking that way, it's flat. If I stand here looking this way, it's all flat across the level. What I do not see is a curve like that. I don't see that at all. It's just dead flat, so therefore it must be flat. Okay, there's a little bit of a problem with this one. The logic behind it is a little bit false, and that is this. If I have a large ball, so we're going to have a large ball, and I take a point of reference here, and I go a certain distance out, and that's it. As I go around, I'm staying that same distance out all the time, and I come back. Essentially, what I've done is I've drawn a cone. That's essentially what I've done. I've drawn a cone. So every point on this part of the cone, for example, is the same distance from this point here. We can all agree with that because we all understand what a cone is and we all understand how a cone works. So in this particular case, we will clear that off and we'll go again. We have a small curve. We have a point of reference, which is a person standing here looking out. They look this way, they hit the horizon. They look this way, they hit the horizon. Now we've just seen that the horizon, according to the calculator, is 3 miles away for a 6-foot tall person. 3 miles to the left, 3 miles to the right. It also means 3 miles out in front, which means they're looking at a curve. So the horizon, everywhere they look, if we are on a ball, will actually be the same distance from where they're standing. As the horizon looks to be the same distance, it is therefore the same height in their eyes, and it will look flat. So whether the world is flat or whether the world is round, going to the shoreline, putting up a level on a trestle, and then looking out at the water to see that it is level, does not actually prove that the world is flat, because the same result would be seen if the world was a globe. So that is number 2 proof debunked. Remember, it might be flat and it might be a globe, but we should not fall into that logic fallacy of seeing an observation, and that is, we have one observation, the water level is flat with the spirit level, therefore everything is flat. Especially considering when the extra information comes to hand, we discover that even on a round ball we would get this same result. Let's move on to number 3. Number 3 is a little bit of an extra additional thing based on number 2. And that is, when we have the water line here, we have a boat on the water. We do not see the boat sail from left to right in this fashion, as it's coming over the curve and going down again. Now here we have a little bit of an issue, we have a little bit of a problem here. Let's assume, for example, that the person standing here on the shoreline, we'll call this the shoreline, they have a 3-mile arc. Okay, this is their horizon, 3 miles. It's not a very good one, but we're just talking about a point of reference. If this ship is within this horizon line sailing across here, technically we would assume that this point is closer to the observer. Yes, we will acknowledge that. This point is further away, therefore should be a little bit down the curve. So we will acknowledge that as well. Now, we can, if we want to, using these sorts of triangle things, and we can work it out with a circle, point of reference, and so on and so forth. But we don't actually have to. The reason we don't have to work out the specific distance here and here, although we could actually do that, the reason that we don't have to do that is because when we accept the equation of curvature, how much curve per distance, how much curve per distance. Now, what we find with that is the following. I just had a great thought here before we move on to that. Seeing as we just did this little calculator thing here, let's go kind of old school. We're just going to go 3, 4, 5. It's not accurate because we know that this is a distance of 3 miles. So we could actually just change it to 3 and then we could make these according. But if we just go 3, 4, 5, I like the idea of 3, 4, 5 because we're going to assume this is 5 miles and then our next observation point here is 3 miles. And we have to compare what sort of difference we would expect to see from this. So let's have a look at that instead. Okay, here's what I've done. I've played around with the viewer height until we have a horizon of 5 miles. So that's pretty well as close as I can get here. So we are 17 feet high, which is 5 point something meters high. So this is much taller than a person would be. And you'll begin to see a little bit of a problem that we have. Okay, so the distance, the short distance that we came up with was the 3. So that ship is sailing right across and it will be 3 miles from us. Okay, so according to this calculator, when it is 3 miles from us, the difference is 6 feet. Now, I ask this simple question. Do you think you will be able to tell the difference of 6 feet at 3 miles to 5 miles when you're looking at this vessel sail from left to right? It is in the ocean. It is 3 miles out. It is 5 miles out. Do you think you will be able to distinguish 6 feet on the hull, considering there are waves in the way, and some of those waves could be 3, 4, 5 feet high themselves? So obviously, no, you will not be able to distinguish a difference in height on any vessel going from left to right of only 6 feet. That is using our little diagram here. The person on the shore sees the boat at 5 miles, they see the boat at 3 miles. There should be a 6 feet difference. However, it's 3 miles away, it's 5 miles away. Who knows how big the waves are in between that? So even if there was a difference visible, such as the world was curved, they would not be able to distinguish the distance simply because of the distance. The height difference would not be distinguishable because the ship is too far away, even with a P900, and the waves in between could be 3 to 6 foot high themselves, which would hide any difference observed in the hull. In other words, the fact that we do not see a ship curve over, come up and go down when it sails within our visual range is not proof the world is flat, because whether it's flat or whether it is round, when it is within our visual range like this, when it's within our horizon line like this, we will not be able to tell the difference anyway. So let's move on to the next one. Okay, one of the next ones, I find it actually a little bit interesting because it doesn't make sense from a flat earth person's point of view when they're applying the logic of the round ball that it's not working on the round ball. But if it worked on the round ball, then it would also work on the flat, which would mean, you'll see what I'm saying. So the logic is this: if the world is round, and if we have this massive huge sun and it's bombarding us with parallel rays because it's so far away and the rays are all hitting us parallel, then the question becomes this. We have this nice little layer of air around the world. So this looks all very nice and well. Then we have this sun's ray that kisses the top of the world and it hits here. And this one kisses the top of the world, keeps traveling, and it hits this point on the clouds and this point on the clouds. So the question then is this: how come when I stand here completely on the dark side, I do not see these lit up clouds over here? Why not? If the world was round, I would see these clouds lit up at night due to this fact. Okay, on the surface that sounds like a logical argument. However, there's a very big problem. That only works when you have a small ball and the distance between the ball's surface and the cloud layer is massive compared to the size of the ball. So let's have a look at this from a round world point of view and see what would we actually be looking at in this situation. So we have a round world, and we're going to have to simplify this a little bit. And what we want to do is, we'll just make this so you can see what I'm trying to do here. This will help tremendously, and then we'll scale it down from this point. Okay, so this is your vantage point here. This is where we have to start with this vantage point here. We have the sun's rays hitting parallel, kissing the top and hitting this cloud over here. Okay, so what we need to know is how far from here to here. This is what we need to know. That will give us our answer, because then logic would suggest we should be able to see the same down this way. Okay, so how we go about this one is we take the center of the ball and we come straight down to the center, which is our observation point. We then also go up to the cloud, which is this point here, and we are again left with a right angle triangle. As you can see, this is the hypotenuse and this one isn't. So then what we do is we take the circumference or the radius of what we are told is the ball Earth. So that will be the radius. To that we add the cloud height. In this case, I'll be generous and say that the clouds are actually 10 kilometers high. but they might only be 4 k's high or 5 kilometers high. And for instance, they might only be 5 miles high, just for argument's sake. They might be 7 kilometers high, something like that. But I'll make them 10 kilometers high. Now, based on this, let's plug in and see how far this distance actually is. So here we are on a right-angled triangle calculator. We want to calculate the hypotenuse. We know B and we know A. We know the hypotenuse and we know B. What we want to do is we want to calculate A. So the B is our radius. B was our radius. Remember, the sun caressed the world, and then it carried on to the cloud up here. So B is our radius. So we plug that in. Now, I'm going to use kilometers here, but it's 6,378 kilometers is the radius. Now, I'm going to make the clouds 10 kilometers high. So we go 6,388. That's what we know. Right angle triangle. I don't need to know the rest. Let's calculate edge A and see what we get. What we get from edge A is 357 kilometers away. So if the cloud is 10 kilometers high in the sky, the furthest I can see it from that vantage point where the sun's rays will hit the cloud is 357 kilometers away. Now, what does that mean? Coming back to our little drawing here, what that means is this. From this point here, where the sun just touches to here, is 357 kilometers away. Which means if we go to the same thing on this side, anything past this, we can't see it. So this will be our observing point. The observing point will be 357 kilometers away. In other words, if the cloud is 10 k's high and the sun is hitting it, you will be able to see it from 357 kilometers away. However, let's go back to the calculator, change the height to only 5 kilometers high, and see what we get then. As you can see, I've already made the change here. 6,383, we'll calculate that. Hang on, we need to remove that because that's going to give us a dodgy answer. 6,383, and we'll just remove all of these as well because we want to just start raw. So 6,378 is the radius. 6,383 is a 5 kilometer high cloud, and it's, well, see, look, it's just making it 10 all by itself. I didn't want that. Let's try again. 6,378, and edge C is 6,383. Now we'll calculate it. Now we're only looking at 253 kilometers away. Only 253 kilometers. That's not very much at all. So 253 kilometers away is the cloud cover. Now let's go to the online calculator. Now the round world is spinning, apparently, if we live on a ball, it is spinning at 1,675 kilometers an hour. 253 goes into that 6.6 times. So if we divided to calculate how fast we are moving, so in 1 hour we have gone 1,675 kilometers. And what I've just done here, I've just cleared everything because I want to show you a different approach. So we're going to say 1,675 kilometers in an hour. So in 15 minutes, we will have traveled, 15 minutes being a quarter of an hour, 418 kilometers, which is further than the 253 kilometers that you would see going by what I've just shown you. So let's just try that again. 1675, let's divide that by a 5 to see a fifth. Okay, so what are we going to get here? Okay, 335 kilometers. So as we keep trying to figure out what time frame, like we can work it out backwards, but how many kilometers am I traveling in 1 minute? So we go 1675 divided by 60 tells us I'm traveling at 27.9 kilometers a minute. So at 253 divided by 27.9, we're talking 9 minutes. In other words, when you see those clouds, they're lit up by the sun, 9 minutes later, they are out of your view. Because if you're on a spinning ball, you've spun away. And so now I ask you to recollect to your own time ever looking at a sunset where the sun is shining on the clouds. Do you see it for an extremely long length of time after the sun has left the horizon line? Or are we only talking 9 minutes or something like that? So let's go back to the original map. Not the original map, but the original drawing here. So at 10 kilometers high, we were looking at 357. At 5 k's high, we were looking at 253. At 253, it's all over in 9 minutes. At 357, I think it was, what were we looking at there? It was about 12 minutes. In other words, if we are on a spinning ball, the clouds that you can see, before you can't see them because you've spun away and it's dark, you have 9 minutes, you have 12 minutes. Because this light coming across a spinning ball will only affect these clouds. So, to the answer, why don't we see clouds at night if we are on a spinning ball? This is the answer why. The cloud height is not high enough, therefore further out enough for us to see. The clouds would have to be out here somewhere for us to be standing here in darkness and see them. And we have no way to calculate, well, I don't have a good, clear way to calculate that, because I would need to then calculate you'd almost need to go perpendicular from this point. So you'd have to go a quarter of the world, then you'd have to take an eighth, and you'd have to go out until this formed a triangle like this, and I'm not going to do that math at all. But in terms of if the world was round, we'd see clouds of night. No, we actually wouldn't, and this is the reason why. Okay, let's move on to number 5. And number 5 is, there is no gravity, there is just buoyancy and density. Okay, now we have there's a couple of different issues here, because there's gravity as the globe people will promote it. So, for example, the globe people will say gravity is pulling towards the center, and it doesn't matter where you are on the globe, beneath your feet is a direct line to the center, so gravity will always be pulling you down. They, using this gravity model, that is, mass is the center where everything will be pulled. The problem with that is that when those people try to debunk the flat earth people, what they are then claiming is this becomes the center of mass, that gravity out here would be pulling you in this way. So if you were to stand on the edge of your flat Earth, you would have to be standing almost like that, whereas in the middle you would be standing up and down like that. Now the problem with this argument from the globe people is that they're assuming that their gravity is based on the center of mass. So that is a logic fallacy, because what if it's not based on the center of mass at all? Okay, so the globe people are wrong when they try to make fun of the flat Earth people by saying this would be the result on a flat Earth, because they are assuming gravity is based on mass and it's all about the center of mass. So let's just try something a little bit different here and you'll see where this is going. We have the ground. For argument's sake, it doesn't matter if this is a flat Earth or a round Earth. Okay, it's the ground. Now, what we do know, for instance, is that a helium balloon will rise, and we know that a bowling ball will plummet. Okay, so we understand this. This here is the air. This is denser than air, it will fall. This is lighter than air, it will go up. Buoyancy and density, case proven. Why are you telling me this is a debunk video? You've just proven the point. I have. However, the one thing that the flat Earth people always ignore is this next bit. For gravity to have, for there to be a buoyancy and a density in this case, we must first have an up and a down. Only buoyancy and density will only work when we have an up and a down. That is somewhere for the dense object to go down to and somewhere for the light object to go up to. So in the case of where you have the 0G plane flies along and it does these parabolic arcs in its flight path, and during this arcing period here where the plane is falling, it's done the arc, everyone inside the plane is floating around. So within the plane itself, you know, there's the windows, here's the floor of the plane. As the plane is falling, the people are falling also, and they, in relation to the confines of the plane, they are floating. So they are weightless within the confines of the aircraft. There is no up, there is no down within this weightless environment. Only when the aircraft does this next curve, starts to go up, the whole body of the plane goes up, but the person's body was falling down, they now hit the floor. So in a case where everything is falling at the same rate, of course we already have up and down, but this is just an example. When everything is like this and there is no buoyancy and density case, a person, a bowling ball and a balloon will all just be bobbing around in this area because they're all falling down at the same rate. Buoyancy and density therefore does not take place within this 0G plane. Okay, so having established that, what then is the problem? The problem is that when you have your land and you have your items which fall to it and you have your items which rise up from it, the flat earth people never acknowledge that there must first be an up and a down, and then buoyancy and density takes place. So while they immediately say there is no gravity, there's just buoyancy and density, well, there must be something to determine up from down. Now here is where we can get into some slight disagreements. Now, the ball Earth people, as I showed, will say it's about the center of mass. And the center of mass is pulling everything towards it through some bending of space-time. I'm not going to get into it. You've got Newtonian gravity, you've got Einsteinian gravity, and while they are similar, they are a little bit different. Okay, so this is their idea. The globe people are saying it's mass. The flat Earth people are saying there's no gravity, it's just buoyancy and density, by ignoring that there first needs to be an up and down. However, we have another school of thought, and that is, we're talking almost like a Thunderbolts project. We're talking like, is it Kevin Williams or Ken Williams, dielectric magnetism type of thing. All we need is a static difference. So when you rub your feet on the carpet, you get that little static charge that jumps from your fingers to your thing. So when we have a bunch of fluffy clouds up here and a lightning bolt happens, the lightning hits the ground. The lightning comes to the ground. So the lightning is going from this point down to the ground. So it's earthing out at the ground, let's just say, which means there's a static differential from up here down to the ground. If that's all you need, you only need to have something to give you a direction of a static differential. Now we have down. That's all you need. We have down. We have up. Once we have down and up established through this static differential, I'm just using this as an example to explain how we can have an up and down. Once we have the static differential up and down, then buoyancy and density play a part. The bowling ball falls to the ground and the balloon with helium rises up. Only once we've got the static differential. And it doesn't need to be a massive one. We just need to have a differential where it wants to go from one to the other. And there you go. So then when we come to the experiment, which you might all know about, he's got a ball and another ball, and this is on a pivot. This is on like a fulcrum point here, and that ball gets attracted to this ball, and he's watching this from really far away through a telescope to see if this moves. Therefore, gravity is based on the two masses of the objects coming together. It ignores the fact that there might actually be a static attraction between these two objects. When you consider that you can have a plastic comb pick up pieces of paper from the table, when you rub the balloon and you place it near a streaming water, so you've got the water tap coming and the water's coming down, and you put the little balloon next to the water and the water bends around the balloon. So this is a balloon bending water due to the static differential. When you can see that that's actually taking place, when you have a comb, you've brushed your hair with the comb and you have lots of little pieces of paper and they all jump up to the comb. These pieces of paper are defying the apparent mass of the world through a small little piece of static differential here. From the table they sit on to the static differential in the comb, the paper flies up to the comb. Now, no one would ever say that paper is an electrical conductor, and yet here we have paper defying the gravity of mass based on a small static differential. So then, to postulate in favour of the flat earth people, if all you have is a static differential from here to here, where everything wants to travel down to equalise, now you've created an up and down, and now buoyancy and density takes place, and it does not matter that the globe people say this mass does not matter. Only the static differential to create the up and down to begin with, and now we're good. So there's a different theory on gravity. So it doesn't matter what you call the force. You can call it a static differential. You can call it a gravity based on mass. It doesn't matter what you call it. There must first be a force to determine up from down before we have buoyancy and density. And that is the problem that the flat earth people never ever address. So let's have a look at all 5 in one hit. So here we are. These are the 5 things that we have covered. The horizon at eye level. We have seen that even whether the Earth is flat or whether the Earth is a globe, the horizon will appear to most people to remain at eye level even when they go up into an aircraft at 33,000 feet or 10 kilometers high. Even though the horizon will not actually be at eye level, it will be that close that it's indistinguishable to a normal person looking out to know if it was actually at eye level or not. The second one, the sea looks flat. Whether we are on a flat world or a globe world, the sea will look flat. So both of these will apply to either flat world or globe world. We will have a horizon at eye level and we will have a flat looking sea. Number 3, ships never sail left to right over a curve. That is, when they come within our field of vision, within our horizon line, we see the ship sail from right to left. We never see the ship go over a curve. And I showed that even within our horizon line of, let's say we had a horizon line of 5 miles, even when that ship comes straight across through our vision, it stays at that initial distance away, and the closest it gets to us is 3 miles, that the difference in height, if we were on a globe, is that negligible that you would not be able to tell if the ship was actually sailing over a curve or not. So again, whether the world was flat or whether it was a ball, the observation would remain the same. And here we are falling into what I said at the start of the video, a logic fallacy. All the people sitting against walls makes you smile. That's not correct. We're looking at an observation. We know it's not correct with the wall sitters, and yet here we don't have any outside extra information to help us. Clouds at night, I showed that the reason we don't have clouds of night, if we are on a ball, makes perfect sense. Now there are other elements to come into play that a globe person might say, well, what about clouds at night on a flat earth? Surely the sun would shine out fully. Well, in that case, I do need to debunk the globe earth people, and I will be doing that in another video because they have explanations that don't make sense as well. And lastly, we have no gravity. There is no gravity, there's just buoyancy and density. And the problem with the flat earth people who present this argument is that they always ignore the one simple truth needed before buoyancy and density plays a part, and that is that you must have an up and you must have a down. Without an up and without a down, you don't have buoyancy and density. And just to reiterate something here with up and down. Okay, so this is a pretty crude test tube. If it is full of blood and we want to separate it, we put it into a centrifuge. And for want of a better explanation, as the centrifuge spins, the test tubes are out. The centrifuge spins around, the test tubes fly out. All the heavy blood cells gather at the bottom and the lighter plasma is at the top. Same on both sides. So that when we slow the test tube down and the test tubes stop, we have all the blood cells at the bottom and we have all the lighter plasma up at the top. And here we have a beautiful example of buoyancy and density within a centrifuge to separate blood. Their buoyancy and density here, though, is this would be down and this would be the up. So the lighter material is up and the heavier material is down, but this was created by the centrifuge forces spinning it out. In this case, the whole point of that is to just show that we need an up and a down before we have buoyancy and density. So that's it for this video. If you have any other proofs either way that you would like me to investigate or possibly debunk, do please let me know. I do have other videos in this series debunking the flat earth proofs, that they are not flat earth proofs. The whole point of this is not to say that we live on a flat earth. It's not to say that we live on a ball earth. My whole purpose here in this video is to point out that the proofs being used are erroneous proofs and often can apply to both globe and flat earths, so they do not actually prove anything either way. They are just an observation that would be made whether the earth was flat or a globe, and that if the flat earth community wants to make better observations, they need to take care of the points that I've raised to debunk the points that I have raised in essence as well. That's it for this video. As I said, do please let me know what you think in the comments below. Anything that you want me to debunk in terms of the globe earth arguments or the flat earth arguments that I will be having a look at. This is just the first 5. I do have others to come. I do have a bunch of globe earth claims that I will be debunking as well in this series, just to show that both sides of this argument do make gross errors within their claims. Anyway, that's it for this. All that's left to say is, like I don't know the shape of Australia because I cannot experience it for myself, I have no individual way to prove beyond a shadow of a doubt to anybody's satisfaction, flat or globe, that we live on a flat or a globe, if truth be known. To be truthful to oneself, that any other evidences I am accepting from other people, I would therefore be taking based on faith, because I do not have the ability to test them myself. Just as I said, the shape of Australia I take on faith, and to realise that we actually do take a lot of other things for granted on faith based on a sense of the authority of the person passing that on to us. Anyway, that's it for this part 1 of the mystery of globe earth versus flat earth. I'll see you in the next one.